Hi, welcome to Organic Chemistry. We're going to continue on our discussion of conjugated pi systems that are acyclic. I'm going to go through this material pretty quickly. I might go back later and put up a more extended recording, but I just want to put up something quick because for those of you in my class, since we have an exam coming up next week and I'd like to get something posted. Alright, in our previous recording we looked at acyclic conjugation, and we saw that when you had a series of double and single bonds alternating, double single, the p orbitals all interacted to make one large set of pi orbitals, pi combinations. So we already knew that if we had two p orbitals on adjacent positions, we made two combinations, a pi and pi star combination. But if we had four p orbitals, we have four sp2 hybridized carbons in a row here, we're going to make four combinations. If we had six, we'd make six combinations. If we had eight, we'd make eight combinations, etc., etc. And we can fill in electrons, and we can see that some of those are filled and some of those are empty, and we were able to draw these orbitals. We were able to decide which was the highest occupied molecular orbital and which was the lowest unoccupied molecular orbital. We also found that these orbitals, this conjugation helped explain several properties that we observed. Alright. I want to look at some of the characteristic reactions of conjugated systems. And the characteristic reactions of conjugated systems are called paracyclic reactions. Here I show four reactions, which in some ways look similar and in some ways look different. Let's just start here on the upper left with cycloadditions. We've actually already seen this when we did alkene chemistry, and I said we'd come back and spend more time on it. This is what we're going to spend most of our time in this section on. But in a cycloaddition, we put two pieces together. So this is an addition. So from the standpoint of, well, really either of these, you're adding atoms and not taking any atoms away. So that's an addition reaction across a pi system, across this, say, this alkene. But you're making a cycle, since the name cycloaddition. Mechanistically, that works by moving electrons around a ring. If two electrons from this pi bond reach out to this carbon, well, this carbon already has 8 electrons, so we got to move 2 electrons away. Let's move 2 electrons to there. But if I share 2 electrons between here, this carbon already had 8 electrons, so let's move 2 electrons away. Let's move these 2 over to here. And that's going to make 2 new sigma bonds, and we've moved the pi bond. Electrocyclizations similarly involve conjugated systems, but in this case we're starting from something acyclic, and we're making a sigma bond to close up the ring. And that involves moving 2 electrons from here to here, 2 from here to here, and 2 from here to be shared between these two to make that new sigma bond. I'm not going to spend much time on sigmatropic shifts, and there's other reactions that also fall in the paracyclic. Here I've shown an ene reaction. Don't worry about these. I'm not going to spend any time at all on these guys. I just want to point out that arrow pushing for these involves moving electrons around the ring. And in fact, all of 4 of these have very similar transition states in which you've got a series of electrons that are at the point of transition state. Bonds are forming and bonds are breaking and electrons are moving around the ring, so that we've got electrons delocalized in a cyclic transition state. All the bond forming and breaking happens simultaneously, so these are all concerted processes. And these are all related, and they're kind of governed by the same physical principles. We're going to spend most of our time on cycloadditions, though I'll come back in part 3 and spend just a little bit of time on electrocyclic ring closure. So, like I said, paracyclics are defined as concerted reactions where all the bond forming and breaking happens simultaneously within a closed ring of interacting orbitals. So, the electrons in the transition state that are changing are in a loop of orbitals that are all sort of aligned around a ring. We're going to focus on the cycloaddition, and in fact we're specifically going to focus on this cycloaddition. This is called a 4+2 cycloaddition, and hopefully the source of that name is obvious. This part's the 4 and this part's the 2, and we're putting them together to make a 6-membered ring. This one is also called the Diels-Alder reaction. That's the name of the guys that discovered it. Or actually, I'd have to look back at the history. At least it's the guys that did the key work in the early years. I assume they discovered it, but if not that, they certainly studied it extensively. And this reaction, as far as it goes, is nice. It's a way of making cyclohexene. But if that was the whole deal, that wouldn't be much, and I wouldn't spend that much time. I wouldn't end up spending much time on this. But we don't just have to have butadiene and ethene. We could have anything that's got this as part of it, and something that has this as part of it. We're going to call this guy the diene, and we're going to call this guy the dienophile, the thing that wants to get together with the diene. Right? Filio is to love. Bibliophile, Anglophile, Philadelphia, book lover, England lover. Philadelphia is the city of brotherly love, right? So the dienophile is the thing that loves the diene. But let's say I had a different diene. Here I've got this species, but it's still got that same butadiene piece as part of the molecule. And here I've got a different dienophile, but it still has that same ethene. It's just got other stuff attached. And if I put those together to make a six-membered ring, I'm going to make a six-membered ring with this other stuff attached, right? Because I'm making a bond between here and here, and here and here, and I'm moving a pi bond. So my Diels-Alder reaction just involves connecting up these guys. But what about this methoxy, this ketone piece, and this methyl group? Well, they're going to end up attached to the six-membered ring. But I'm specifically going to draw this structure. Now, if I was putting together these two and just making bonds, I could actually make a total of 16 possible stereoisomers and regioisomers. So these guys all involve taking a piece from the diene and a piece from the dienophile and putting them together. But notice I varied up the stereochemistry, and I've also varied up made constitutional isomers, because if instead of connecting this guy up like this, if I flip the dienophile over 180 degrees, I'd get a piece that look like this. I can make all of these guys and then the mirror image of all of these guys. So that's a total of 16 possible isomers. But of those 16 possible isomers, we only make two, this guy and the mirror image of this guy. So we make a racemic mix of this and the mirror image. All right, let's go through and see if we can understand why we get specifically these products. It's going to be based on electronics, and we're going to discuss regiochemistry, that is really which constitutional isomer is formed, and stereochemistry, that is which set of cis and trans disubstituted, well, trisubstituted, the relative stereochemistries of these various stereocenters. Why I picked the one that I show. First, and this would really benefit from pulling out your model set and imagine bringing these things together. Let's just quickly go through. The orientation of reactant is such that if I'm bringing ethene and my diene and my dienophile together, they're not going to come together in kind of a totally coplanar fashion because they'd bump into each other and because the p orbital wouldn't interact. What's really going to happen is they're going to come together where one's kind of above and the other below, or we could also have the ethene come from above. And that's going to allow us to not have these hydrogens banging into each other. And also, as I approach this guy from underneath or from above, the p orbitals from my dienophile will overlap to interact with the p orbitals of my diene. And those overlapping p orbitals are ultimately going to become the new sigma bonds with some rehybridization. But I didn't draw in any shadings, any phases on the p orbitals on the previous slide. What happens in a reaction is the highest occupied molecular orbital of one comes together with the lowest unoccupied another. So, for instance, here's the highest occupied molecular orbital of my diene and the lowest unoccupied of my dienophile. And if I brought those together, so let's kind of wrap this up in the conformation that it's reacting, notice that this shaded overlaps with shaded and unshaded overlaps with unshaded. This is going to be a favorable process. Okay, so we can do this reaction. I want to compare and contrast this with a 2 plus 2. Here would be a picture of a 2 plus 2 cycloaddition, and you could draw curved arrows showing that you could go from here to here. And they're very similar to the curved arrows here. Pi electrons go here, pi electrons go there, we make a square. But let's consider the highest occupied and the lowest unoccupied. So if I had the highest occupied of one ethene and the lowest unoccupied of the other, if I put those together, yes, this overlap is in phase, but this overlap is out of phase. So this overlap is bonding, this overlap is anti-bonding. Bonding and anti-bonding cancel each other out, and therefore this reaction doesn't happen. And it's not just that this one makes a square. You might say, well, squares are strained. Cyclobutanes are strained rings. It turns out that it has to do with the orbitals. And if we can look at other ring sizes as well, we're going to see a similar story. Okay. But back to the Diels alder. If we're interacting the highest occupied of my diene with the lowest unoccupied of the dienophile, I've just shown you that the orbital phases work out so that it's all bonding. But orbitals interact best when they're closer in energy. And here, these two guys are kind of far apart in energy, because remember, this is an energy scale, going from the bottom of the page to the top of the page. If I could raise the energy of this guy and lower the energy of this guy, that would make for a more favorable interaction. So let's take these orbitals and let's tweak them a little. And it turns out that if I add in electron donating group, EDG stands for electron donating group, and electron withdrawing groups to these, they will respectively raise and lower the energy. Electron donors raise the energy of orbitals, and electron withdrawers drop the energy of orbitals. What are electron donating groups and withdrawing groups? Well, for instance, a methoxy is an electron donating group. I can draw a series of resonance forms. If I've got a lone pair adjacent to a pi bond, I can draw a resonance, and then I can draw another one. And notice that if I look at the 4 carbons of the diene part, it's got some amount of partial negative in this case. So this is more electron rich than plain old butadiene. Anything with lone pairs adjacent to the pi system would act as an electron donor. So we can see here, or here, or here. On the other hand, if I had, for instance, an aldehyde adjacent to a pi system, I could draw a resonance. Electrons go here onto the oxygen, and that puts a plus charge adjacent to the pi system. And when I've got a plus charge adjacent to a pi system, I can draw a resonance. And now if I focus on these 2 carbons, there's some amount of partial plus. And so these are more electron poor than just ethene. Just focusing on these 2 carbons, they're more electron poor on average than ethene. Anything that puts a partial plus or a plus adjacent to a pi bond acts as an electron withdrawing group. So things like this are electron donors, and even a methyl group is a slight electron donor. And things like carbonyls or nitros are electron withdrawers. Okay. So my dienes will react best when they've got electron donating groups, and my dienophiles react best when they've got electron withdrawing groups. And when we got both, we get the best of both worlds. But now that I've put substituents on my diene and my dienophile, we run into the question of regiochemistry, because I can bring these 2 things together with 2 different orientations. If I flip this piece over, I'm going to make this orientation, but if I connect bonds here and here, I'll make this isomer. If I connect them here and here, I'll make that isomer. I can predict which will be favored based on those resonance forms that we just showed. I just showed you that if I had an electron donating group, resonance allows me to put a partial minus here and here. If I've got an electron withdrawing group, I get a partial plus here or here. Which of these 2 is better? Well, the one that brings opposite charges closer to each other in the transition state. So as this molecule is coming close to this molecule, there's going to be a favorable Coulombic interaction in this case, because opposite charges attract. Partial minus is attracted to a partial positive. So as we approach the transition state, there's going to be a favorable interaction in this case that's not present in this case. It's not that this one's horrible, it's just that this one's better. And as a result, what we're going to see is that this orientation will be preferred, and we will observe this isomer, constitutional isomer of product. This is called the 1,2 product, and this is called the 1,3, just in terms of, counting around the ring, starting from this 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, and we will observe 1,2 product, not 1,3 product. But that's based on having an electron donating group here. I could also put a substituent here. So let's consider the case where I've got my electron donating group on the 2 position of the diene. Again, we can make 2 isomers potentially. But if we did that same analysis where we considered where the partial minuses and partial pluses were, this pairing gives us the best overall energy as we approach the transition state, because there's going to be a favorable stabilizing interaction between a partially negative center and a partially positive center. And so, experimentally, what we observe is that we get this isomer, not this isomer. This isomer is the 1,4, and we don't observe the 1,3. So notice between these two examples, we saw 1,2 product and 1,4 product, but we don't ever see 1,3 product in the Diels-Alder reaction. That's regiochemistry. Okay, a second thing to consider is just the diene itself. This is a little less important, but let's just quick notice that to bring these guys together, in the transition state, we got to bring this carbon close to that carbon and this carbon close to that carbon simultaneously. And we can only do that if we've got the S-cis conformation of our diene. If we have the S-trans conformation, we can't bring these guys close to each other simultaneously. And even if you did, even if you just kind of stretched it, you'd end up with a trans double bond. It wouldn't work. This just sterically is too strained. As a result, this is going to have an effect on what dienes work. This guy and this guy are both dienes, right? They both have 4 carbons in a row that are both pi bonds. But in this case, they're kind of, because of being part of a ring here, they're locked into an S-cis conformation. In this case, they're locked into an S-trans conformation. So this guy works really good. This guy doesn't work at all as a diene. These guys in the middle, I have rotation around this bond. This guy, for steric reasons, doesn't really like being S-cis. As we go from towards the left, we get better and better. So the more able we are to achieve an S-cis conformation, the more readily a Diels-Alder can happen, is the lesson here. Okay. Stereochemistry. Let's consider the dienophile. So here's my dienophile. In this case, I've just got hydrogens. So it doesn't, matter. But what if I substituents? What if I've got 2 R groups? Let's say I've got a cis diene, or a, Z alkene. In the transition state, notice as this guy is coming close to that guy, these guys are facing the same way. And if I form my bonds, they're still facing the same way, because this is a concerted process. All the bond forming happens simultaneously. This stereochemistry is preserved. So if I have a Z alkene at the start, I will have a cis disubstituted ring. If dienophile is E, these 2 groups are away from each other in the dienophile, in the starting material. As these things approach each other, these 2 R groups are still far away from each other, opposite sides. And then if we simultaneously make bonds here and here, these 2 sigma bonds, these 2 R groups are still on opposite sides. And so if we start out with a E, or trans, alkene as our dienophile, we will get a trans disubstituted product. So the dienophile stereochemistry is preserved. If it starts out cis, it ends with cis substituents. If it starts out trans, it ends with trans substituents. But what if I've got a substituent on my diene and a substituent on my dienophile? Here, it's going to depend on the orientation. As this dienophile comes close to the diene, does it come with this orientation or this orientation? Notice the difference here. This is called exo, because the R group is away from the pi system of the butadiene. And this is called endo, because the R group is underneath. It's in towards the pi system. And they lead to different stereochemistries. If it came together one way, it would give us this relative stereochemistry. If it came together, so that was exo gave me this guy, endo gave me this guy. So one gave me trans and one gave me cis. So we go into lab and we find out that one of these is preferred. And it's going to come down to this. Our R group, our substituent on dienophiles, is generally electron poor. Partially positive. Remember we said a positive or partial positive adjacent to the pi system makes for a good dienophile. Well, in the exo configuration, that partial positive is away from our pi system, which remember is partially negative. On the other hand, if I've got an endo arrangement, this partial positive is close in to this partially negative electron-rich pi system, and it turns out that's perfect. And so what we're going to see generally is the endo orientation is best, and that's going to lead to a specific, or that's going to selectively lead to a relative stereochemistry. What about absolute stereochemistry? That's going to depend on whether my dienophile comes from below or above. On the previous slides, I was saying plus minus, right? I wasn't defining which specific enantiomer. But if I come from below, and if you built a model of this and a model of this, you would see that that leads to this enantiomer. If this dienophile came from above the diene, we lead to the mirror image. Well, these are flat. This guy's a flat thing and this guy's a flat thing. If you bring together like two pieces of paper, they're equally well, they're going to interact the same if this guy's on the bottom or if this guy's on the top. And it turns out that as far as absolute stereochemistry goes, absolute stereochemistry means, okay, will we have R or S? We're going to get a 50-50 mix. They're going to both be cis, so we won't get the other stereoisomers where this one's back and this one's forward, or this one's forward and this one's back. But from this diene and dienophile, we're going to get a racemic mix of these two cis disubstituteds. Alright, so that's the Diels-Alder. When bringing together things, you should be able to predict what product will be formed in terms of the regiochemistry and the stereochemistry, those different aspects. Diels-Alder is very important. It's used in synthesis a lot, and the reason is because it's a great way of making six-membered rings. Six-membered rings are very common in nature because of their stable ring size, and in addition to making six-membered ring, this allows you to control the relative positionings of different groups. Just to give an example, there's this book, Nicolau's Classics in Total Synthesis. It has 37 different large molecules that are synthesized, and 32 of the syntheses use Diels-Alders. And so this is a commonly used reaction in the synthesis of large molecules. Just to give one example, this is Taxol. It's a drug. It's effective as in chemotherapy for certain types of cancers, but unfortunately, it was originally discovered in the bark of the Pacific yew. A lot of our drugs initially come from natural sources. We talked about in class about the example of aspirin, initially derived from the willow tree, chemically modified from a compound found in the willow tree. Well, this is an effective chemotherapy agent, but unfortunately, you have to cut down a tree to get it. And it'll take one tree will equal one dose for one patient, which means you'd have to chop down a forest just to save one patient, let alone all the cancer patients. So here's where organic chemists come in. Can we make this thing in the laboratory? And we can, and there are various syntheses out there for this. And I just want to point out a small aspect of one synthesis. If you look at Taxol, it's got two six-membered rings in it, and we've just seen that six-membered rings can be made with Diels-Alder. I won't go through the detail of this, but in the retrosynthetic analysis of a particular synthesis of Taxol, it involves two Diels-Alder reactions. A diene and a dienophile can come together to make a six-membered ring, which ultimately becomes this blue portion of Taxol. And here's a diene and dienophile, it looks a little bit different. But still, if you follow the red parts, this and this get together to make a 6-membered ring, and that 6-membered ring is this 6-membered ring. Yeah, some of the functional groups have changed. This double bond has been reduced, or there's been an addition across this double bond. But ultimately, these two 6-membered rings come from diels alders. And that's a relatively common motif in complex syntheses. All right, let's go back to that 2 plus 2. Remember we said that the 4 plus 2 reaction works and the 2 plus 2 doesn't. But that's just thermally, if you heat these up. But let's look at two reactions. Here's a particular reaction that when you shine a light on this molecule, a reaction occurs. If we ignore everything that's not changing, the only thing that's changing is here's a double bond and here's a double bond, and in the product there's a 4-membered ring. Or I'll highlight those pieces in red. These two double bonds, these two ethenes get together to make a 4-membered ring. That appears to be a 2 plus 2 cycloaddition. Or here's another one that's got some significance to us. These are both thymine. They're part of your nucleic acids. And if you are exposed to UV light, if you're overexposed, you go out in the sun, you don't wear sunscreen, you can have some of those guys will have a 2 plus 2 cycloaddition happen to make thymine dimers. This is going to mess up your DNA. Too much exposure to light can lead to melanomas. If too much DNA damage accumulates and leads to cancer, right? That's why you wear sunscreen and you don't spend too much time out there at the beach without some sort of covering. This reaction again appears to be a 2 plus 2. Your body does have mechanisms to get rid of damaged parts of your DNA and fix them. It's when you overwhelm those systems, that's when you lead to problems. So don't worry, you're not going to, have problems just walking from class to the car or whatever. But if you spend too much time without, you can cause damage to your body. These reactions are 2 plus 2s, but we just said 2 plus 2s don't work. But notice the difference between what we said before and this. These involve UV light. What does UV light do? Remember, when we talked about UV-vis spectroscopy, we said that ultraviolet light takes an electron from the highest occupied molecular orbital and it kicks it up a level. That is, here's ethene. If I have 2 electrons in my highest occupied molecular orbital, if one of them gets excited, so I'm in an excited state here, eventually this can fall back down to the lower level, to back to the ground state, but some of my molecules will be in their excited state. Okay. For my ground state molecules, this is my highest occupied and this is my lowest unoccupied molecular orbital. But in this molecule, that's my highest occupied. Remember we said the cycloaddition involves the highest occupied of one coming together with the lowest unoccupied of the other. We also said that these reactions work best when orbitals have similar energies. Notice the highest occupied of this guy has the exact same energy as the lowest unoccupied of this guy, because it's the same orbitals, I've just filled in the electrons differently. And so let's imagine this orbital getting together with this. If we did that, the highest occupied with this and the lowest unoccupied of this, notice, hey, shaded overlaps with shaded, that's bonding. Unshaded overlaps with unshaded, that's bonding. This is all good. So the 2 plus 2 works photochemically, but not thermally. The 4 plus 2 works thermally, but not photochemically. If we went through and did an electron, you looked at electrons in the 4 piece or the 2 piece in a 4 plus 2, it turns out that if we have an excited state of 1, it won't work. We can go through and ask ourselves about other reactions, and it turns out the 4 plus 4 works photochemically, and if we analyzed the orbitals involved, we would find that to be true, and the 6 plus 4 works thermally. I'll let you go through and work those out yourselves, but consider, for thermal, consider the highest occupied of one and the lowest unoccupied of the other, and see if they work or don't, and you'll find they work for this one and they don't work for this one. And for photoexcited, imagine photoexciting one of the 2 molecules. So essentially you're going to, instead of consider for the highest occupied, you're going to consider the next one up. because you've moved one electron up, and then do the highest occupied of one and the lowest unoccupied of the other, and you'll find that this one works photochemically and this one does not. Woodward and Hoffmann were two prominent chemists who studied this in detail, and they found that there were patterns that they observed. And it comes down to the number of electrons that are moving in the transition state. Those things with 2, 6, 10, 14, 16, 2, 6, 10, 14, 18, 22, etc. So this pattern going up by 4 each time. Electrons moving in the transition state. Notice these are all even because you got pairs of electrons moving, right? We're not talking about radical reactions. So we've got an even number of electrons. If it follows this pattern, those cycloadditions work under thermal conditions. On the other hand, if you've got 4, 8, 12, 16, 20, 24 ad nauseum, those work photochemically. This can be explained in terms of the orbitals, and this work earned the Nobel Prize for Hoffmann. Woodward had passed away by that point, and Nobel Prizes are not given out posthumously. Don't worry, he got one for the synthesis of vitamin B12, so, you know, he certainly got his due. He's certainly a significant chemist who's involved in several major stories: multi-step synthesis, organometallics, and the physical organic of paracyclic reactions were all things on Woodward's shoulders. Fukui was another chemist who did a lot of work on using an FMO explanation, a frontier molecular orbital explanation, to describe the patterns that Woodward and Hoffmann described. They had a slightly different explanation, a little more complex. They're both good analyses. They kind of focus on different aspects. And these patterns are called the Woodward-Hoffmann rules. What we're going to find is that other paracyclics also have patterns that Woodward and Hoffmann also described. But we're going to look at one of those types of paracyclic reactions in our next presentation. All right, thank you.